Today we're going to be meeting with an old nemesis once again. In a previous video we tried to prepare cyanogen iodide, and ended up with a huge toxic mess. So we figured that this time we'd ignore the textbook and do it our own way. What could possibly go wrong? We vowed not to do this again, but curiosity got the better of us. This is not exactly home chemistry, and we really strongly advise that you don't try this. Our starting material is this, a mixed alkali cyanide salt containing sodium and potassium cyanides in a 1:2 ratio. This sample is a little old and so it has a slight ammonia aroma due to some hydrolysis. It should be okay for our purposes. A safety reminder, this is a powerful poison, fast-acting, and if you let it get into contact with acid then it's going to give off deadly toxic gas. But luckily for us it's also pretty reactive, which means it's a useful and important reagent in chemistry. 1/4 gram is generally considered to be the likely lethal dose for alkali cyanides. Not a lot, but then again, not enough to be trembling with fear. Treat these compounds with respect and caution, take time and care, and they reward you. 2 grams of mixed cyanide salt. The corresponding molar amount using the correct average molecular weight is shown here. Okay, so cyanogen iodide is prepared from an alkali cyanide by adding iodine. One atom of iodine from the iodine molecule goes and forms the corresponding alkali iodide, and the other hooks up with the cyanide and forms the cyanogen iodide compound. So here's our stoichiometric amount of iodine. 8.5 grams. We want to use dry reagents so we're using the commercial iodine pellets as you can see. Here's our theory. We were kind of inspired by Nile Red's iodine video but we had a brainwave. Iodine vapor can easily spread across the alkali cyanide salt surface and probably react quite easily to form the cyanogen iodide. This in turn also has a high vapor pressure and will potentially be able to be collected by a crude condensation type process. In other words, dump everything in a beaker, mix, heat, and put an ice bath on top. Life's too short. Maybe it is now. Let's try it. Here's our iodine. And the mixed cyanide salt. Well, there's no obvious reaction even after standing for a minute or two. So to assist the mixing we're going to add a couple of drops of water. Just enough to slightly wet the mixture. Interestingly, this seems to provoke a reaction as the mixture on shaking becomes much more liquid. Okay, well that's our reaction mixture. So let's get our cooling device on. It's just a round-bottomed flask filled with some ice and water. Heating on. Ventilation is available if we need it, but we'll see. One characteristics of cyanogen iodide is that it's got a strong, highly irritating odor, so it should be obvious if any is escaping. First thing we notice is some purple iodine vapor. And then quickly forming, it looks like we've got white mold-like looking crystals growing on the sides of the beaker and on the flask. Merry Christmas! There's actually a miniature snowstorm of cyanogen iodide crystals inside the beaker. As we let the reaction proceed, there seems to be some discoloration of the crystals on the flask and towards the bottom of the beaker. And we're losing some product from the top. It's snowing cyanogen iodide. So we start the process of harvesting the crystals from the cleaner zones of the flask and beaker. Ventilation time. And then we keep going. More white fluffy crystals are formed, and we harvest them occasionally. Isn't that beautiful? Towards the end we're getting a more yellow-colored product, possibly due to some decomposition, or maybe an iodine impurity in the crystals. There's still a lot of product in there though. The snowstorm is still underway. We collected the more pure-looking crystals, and then stopped the process once we had enough to play around with. Ventilation is still on, although the product is not as bad as we expected. It's got a strong bleach-like aroma but slightly more irritating and definitely irritating to the eyes, but weaker than bromoacetone or benzyl chloride. Very fluffy crystals. 0.68 grams in total though, which is only a 12% yield on the starting materials. But this is our first try, so it's likely that this method can be improved on. There's still a lot of discolored material in the beaker as well. Now we've finally got a relatively pure sample, we can do some experiments and check out its properties. Let's add some water to a few crystals left in the watch glass. Looks to be slightly soluble in pure water. No dark color or iodine forming, at least not right away. So let's try a few more reagents and see what happens. Here's some 30% hydrogen peroxide solution. Cyanides tend to be reducing agents, so we'd expect a reaction here. But there's nothing obvious happening. The cyanide covalently bonded to the iodine in the molecule isn't acting like a regular cyanide ion. It's perhaps more like an organic nitrile compound. A bit goes into solution, but that's all. Time for a new solvent, dichloromethane. If this is a covalent molecule then it should be much more soluble in something like this. Immediately soluble, and a slight pink color probably because of the iodine impurity in our product. Let's do something a bit more crazy. Can it be reduced? Sodium borohydride. Don't ask where we got this. There's a reaction and the borohydride is fizzing away, probably producing hydrogen. However, it's also producing some hydrogen cyanide gas. So be careful if you want to use this compound in a reducing environment. Okay, next up, concentrated sulfuric acid. This is an oxidizing agent and dehydrating agent as well as being a strong acid. There's a reaction, and a little bit of iodine color generated temporarily. Very unlikely that the cyanide group would survive this oxidizing condition though. Let's do it on a lighter background. Okay, well that's not especially exciting, but it's interesting that we're not getting elemental iodine back. In the end we just end up with a faintly pink solution again. Okay. One last test. Cyanogen iodide is what is known as a pseudo-halogen. Let's see if the iodine in here acts in a similar way as though it was elemental. Here's a small amount of aluminium powder. We'll add some DCM to make up a nice strong solution of cyanogen iodide. So let's see if it will react with the aluminium powder. We wait. And wait. But even after an hour there's no visible sign of a reaction. More proof that this compound isn't acting at all like iodine, iodide, or a cyanide ion. We've still got lots left, so we'll probably just store it in the fridge and see if it is stable over time. 2 weeks later and it's still the same. So this preparation method was a success and got us what we didn't get from the first method we tried. It was also a lot more pleasant and didn't result in horrible decomposition products. Our advice is keep this away from organic materials because they seem to accelerate decomposition dramatically. We're not sure if this has any interesting follow-up reactions, but we're sure you'll let us know in the comments. We cleaned up the reaction beaker simply by adding water and then an excess of sodium hypochlorite bleach. This firstly destroyed any residual cyanide, rendering it non-toxic. It also then oxidized the iodide salts produced in the reaction back into solid elemental iodine, which we recycled. So we lived to tell the tale. We were surprised that the product in relatively pure form was apparently quite stable, and wasn't actually that unpleasant to handle, unlike that some of the references had suggested. Most of the weight of the compound is iodine, so it's not at the same toxicity level as an alkali cyanide salt. But the bleach aroma tends to be overpowering, so do use ventilation for any reactions and experiments. And be careful with reducing agents. That's all for this video. As always, stay safe and stay tuned.